3D object detection is important for numerous applications including autonomous driving. It is challenging not only due to data sparsity and irregularity, but also due to dataset size, extreme foreground-background imbalance, and class imbalance. We propose to learn a subset of scene elements, which are meaningful for detection. For instance, given this cyan scene, we learn to select the salmon points, such that both types of imbalance are addressed. There are few background points, more points on cars, and almost all the points on pedestrians. We propose a novel, meaningful, voxel selection method, GraVoS, as well as a new training procedure. We demonstrate improved performance of 4 detection methods, successfully coping with all 3 challenges. 3D detection methods can be categorized into grid-based and point-based. Grid-based methods first transform the given point cloud into a regular representation of either voxels or a 2D bird-eye view. This enables utilizing 3D or 2D convolutional networks, respectively. Point-based methods extract features directly from the raw point cloud, usually by using PointNet-like architectures. Our work focuses on voxel-based detectors. We propose a novel subtractive approach, which provides a further boost in performance to voxel-based 3D detection methods. Given a point cloud scene, voxel-based detectors start by converting a given cloud into a voxel grid. Then, non-occupied voxels are removed and the points in every occupied voxel are grouped. These voxels are then fed into a detection network. The detector outputs both bounding box proposals and class predictions. We propose to add a selection component to this general approach. The goal is to select the meaningful voxels and to remove the less meaningful ones from the scene, in a manner that addresses the 2 imbalance challenges. Meaningfulness is indicated by the magnitude of the gradients, as the gradients encapsulate information regarding the detector's success. Selecting the voxels with high magnitudes puts more emphasis on the voxels that determine the locations of the objects. This key ideas are realized in GraVoS, as follows. The given input point cloud, in cyan, is voxelized and fed into any pre-trained voxel-based detector, denoted as F, at 2 different training stages, early and late. These detectors' losses are computed and are the input of GraVoS, which performs voxel selection. The selected voxels, in salmon, are then fed into the late detector, initializing its weights where it left off and continuing training using the selected voxels exclusively. We will now focus on GraVoS. Recall that GraVoS aims at selecting meaningful voxels and discarding the less informative ones. Given the input voxels and the pre-calculated losses, for each detector, the gradient's magnitude is calculated, and the meaningful voxels are extracted. The selected voxels, highlighted in salmon, from the 2 stages are then merged to form the final selected subset of voxels. This selected set will be used for fine-tuning a pre-trained detector for detection improvement. Next, we will elaborate on 2 issues: the need of the 2 training stages of the detector, and the intuition behind using gradients for voxel selection. We use 2 different training stages since they provide complementary information regarding voxel meaningfulness. The late stage detector assigns higher values to meaningful and unique voxels and lower values to meaningful voxels in repetitive and easy to learn features. Conversely, in the early stage detector, these easy features still maintain a high gradient magnitude. Though learned early on, they are essential for recognizing the objects. Next, to understand the intuition behind using gradient magnitude to determine voxel meaningfulness, look at this image. Given an input point cloud, in cyan, to the left, the magnitude of the gradients is depicted as a color map from blue to red, to the right. Essentially, the gradients encapsulate information regarding the detector's success, which is the location where an object is likely to appear. In our example, the gradients of the background are colored blue. Most of the points on the 3 vehicles are between green and red, and the pedestrian is red. As a result, the selected subset shown in salmon on the right has very few background voxels, relatively more voxels on the prevalent class of vehicles, and almost all the voxels on the less prominent class of pedestrians. To evaluate the performance of our method, we compare state-of-the-art 3D object detection methods on the well-established KT dataset, with and without our GraVoS. This table shows that continuing to train 4 prominent 3D voxel-based object detectors with GraVoS selection yields improved performance on average. The 4 detectors are voxel RCNN, second, part A2, and centerpoint. Furthermore, GraVoS is especially beneficial for the non-prevalent classes, i.e., pedestrian and cyclist, but might slightly degrade the results of the prevalent class car. This is attributed to the selection process, which prefers the non-prevalent classes. In the paper, we report on 6 types of ablation studies. They include the study of voxel selection alternatives, class-level voxel balancing with GraVoS, voxel selection ratio, intra-detector ratio, early-stage detectors training duration, and early and late detector mechanism choices. Today, we will focus on the former 2. GraVoS is compared to 3 other alternatives for different voxel selection ratios. The baseline is the constant performance of the detector, all voxels. It can be seen that, when too few voxels are used, the detector misses objects, as expected. For larger ratios, GraVoS outperforms other approaches significantly. This is due to the fact that we use the meaningful voxels. This figure shows the average number of voxels with and without GraVoS. The background has significantly more voxels than the foreground and accordingly, significantly higher voxel reduction. Zooming into the foreground to the right, the car category receives most of the voxel reduction. Thus, GraVoS effectiveness may be attributed to data balancing. To conclude, our paper presents a novel and generic voxel selection method, GraVoS. The key idea is to select voxels based on their meaningfulness to the detector. GraVoS addresses the challenges of class imbalance and foreground-background imbalance. We propose a training procedure to improve 3D detection without additional data, by utilizing the selected voxels exclusively for fine-tuning. We demonstrated a boost in performance for 4 state-of-the-art detectors on 2 commonly used benchmarks.